Hello, calculus fans. All right, we spent a lot of time this semester computing derivatives. We're now going to work on the problem going in the reverse direction. So we're going to be given a derivative of an unknown function. We want to figure out what that original function is. A good physical application would be where we know the velocity of an object and we want to compute the position function, because the velocity is the derivative of the position. So we're going in reverse, and this is computing antiderivatives. So we make a definition to say that a function f, big F, is called an antiderivative of little f on an interval I if big F prime is equal to little f for all x in the interval. We've actually given this definition before. Now we're actually going to compute some antiderivatives. The basic way that we're going to compute antiderivatives is work our differentiation formulas in reverse. So for instance, we already know that the derivative of x cubed is equal to 3x squared, and so we can put that around in reverse and say that x cubed is an antiderivative of 3x squared. Now it's very important to note the language that we're using. We're going to say an antiderivative as opposed to the antiderivative, because a function can have many antiderivatives. So in fact, x cubed plus 162 is another antiderivative. And that's because when we differentiate x cubed plus 162, we still get 3x squared. Now, quite a while ago, we actually discussed the following theorem. We actually said that if big F is an antiderivative of little f on some interval I, then the most general antiderivative of little f is big F of x plus c, and c is just some arbitrary constant. So that's how we can find the most general antiderivative. That is to say, every antiderivative of little f will look like this. And this was actually a consequence of the mean value theorem, although we didn't go into a whole lot of detail about that at the time. Okay, that's all for now.